Welcome to Microlecture 36. We're going to introduce nucleophiles, electrophiles, and the SN2 reaction. Okay, so I'd like to introduce you to a term called nucleophiles, which, when you break it down, means nucleus loving. Philes means loving. So these are electron-rich atoms or groups of atoms that would like a positive charge. And so we're going to look for lone pairs of electrons, and also pi bonds could be another indication that we have a nucleophile. So here are some molecules below. Pause the video and try to figure out which atom or groups of atoms is going to be able to donate its electrons. Okay, and so if you guessed that the pi bond here is nucleophilic, you'd be correct. It's an electron-rich region of the molecule. Also, the lone pairs on oxygen are an electron-rich region of the molecule. And the next one, we have a lithium, which is a metal. And so immediately when you see a metal, think partially positive. That's not going to be nucleus loving. Because it itself bears a partial positive charge, so it doesn't want to attract a positive charge. The atom that it's connected to, since it's partially positive, must be partially negative. So when a carbon atom is attached to a metal, it's called an organometallic. What happens is the carbon that is directly attached to the metal has a more negative charge than most carbon atoms do. And so this is the nucleophilic atom right here, this carbon, because of its partial negative charge. The lone pair on nitrogen is indeed going to be nucleophilic, so it would attack a positive charge. And lastly, when you have a CN triple bond, even though, we do have a lone pair sitting here on nitrogen, the formal 1 positive charge is on the carbon atom. And so it's really the carbon atom with its excess electrons that is nucleophilic. And so we have the carbon-carbon pi bond. In this case, it was the oxygen. In this case, it was the carbon atom. In the fourth case, it was the nitrogen, and lastly, it was a carbon atom. So the strength of a nucleophile, because not all nucleophiles are the same, is going to depend on a couple of things. First of all, polarizability. So polarizability is, I like to think of it as squishiness. So if you're looking at a periodic table, and you see that nitrogen is above phosphorus, think of the atoms that are closer to the top of the periodic table as being smaller, and the more you move down, the larger the atomic radius, and the more squishy the atom is. Really what's happening here is that the electrons are held out farther away from the nucleus, and so they're more able to distribute their electron density unevenly. All right, so larger atoms are more polarizable, and that's going to make them better nucleophiles. There's a couple of other trends on the periodic table that I'd like to take note of, and so there's the oxygen-sulfur, where oxygen is smaller, sulfur is bigger, and then there's the fluorine, chlorine, bromine, and iodine. So if fluorine was a marble, chlorine would be a tennis ball, bromine would be a basketball, and iodine would be a beach ball. Iodine, always think of iodine as a beach ball. It's very squishy, it's very polarizable, and it makes for a wonderful nucleophile. So that said, if we're comparing the two molecules, one with an SH group and the other with an OH group, and thinking about how much these molecules are willing to donate their electron pair as nucleophiles in order to attack a positive charge, we would say probably we would go with the sulfur as being the stronger nucleophile. Right, and that is an issue of polarizability, and sulfur is larger, more polarizable than oxygen. So these are comparisons within one column of the periodic table. As you move down the column, the atom size is larger and the atom becomes more polarizable. Another definition, by the way, of nucleophile is going to be, that we'll encounter later on as we are distinguishing between different types of reactions, is going to be that nucleophiles love to attack carbons. And so this sulfur is more likely to attack a carbon atom than the oxygen. And not just any carbon atom, but a partially positive carbon atom. All right. And the other thing that, the other factor that goes into the strength of a nucleophile is how available are the electrons for donation. So we have two molecules to compare here. One, the lone pair on oxygen is a bit less available. Why might that be? See if you can think of why. And so if you guessed that it's resonance, you're correct. Here we have resonance stability, making this less reactive. Whereas over here, this lone pair of electrons is more apt or more able to attack a carbon atom. All right, so more reactive. Okay, and so the compound on the right-hand side in this case would be the stronger nucleophile. Let's think now about electrophiles. If nucleophiles are nucleus-loving, electrophiles are electron-loving. And so take a look at the structures below and see if you can figure out which atoms would be electron-loving. These are atoms that would be electron-deficient, or they would carry a positive or partial positive charge. Alright, so wherever I see an electronegative atom, I'm going to put a partial negative. Being doubly bound to an electronegative atom makes this carbon atom the most delta plus carbon atom in the entire structure. And so that is why I'm going to select that particular carbon as being the atom that's the most electron-loving. Okay, it's going to attract electrons because it's so positive or partially positive. Likewise, I see a very polar bond here, and the iodine is pulling on electron density, pulling away from this carbon atom, making that carbon the most electrophilic or electron-loving atom in this molecule. Last one, well, we're seeing the same scenario that we did in the first example where we have a carbon doubly bound to an electronegative atom. All right, and so I would say that this carbon atom is certainly going to be electrophilic, but I have another equally good choice in this structure, it turns out, because of the alternating double bond, single bond, double bond. Remember, we call that conjugation. That means that we have a couple of resonance forms that we could consider here when deciding if the atom involved the carbon atom involved could be electron-loving or electrophilic. Right, so I could just break this isolated carbon-oxygen bond to generate a very minor resonance form, and I'm only going to do that for illustrative purposes. So we can definitely form this and then show the other resonance form that allows us to pinpoint another very electron-loving carbon atom. Now we've identified another equally positive carbon atom in the structure through resonance. So do this activity a lot. Do evaluate resonance, especially in conjugated systems, because it turns out that this carbon atom right here is just as good of an answer, if not better, than the original carbon atom that was attached to the oxygen. Right? So we have two very electrophilic carbon atoms in that last structure. Let's kind of tie all of this together into a reaction that involves a nucleophile and an electrophile. And so this is going to be our introduction to SN2 type of reactions, which is going to be the next video. So I am going to identify a nucleophile here. I'm seeing a negative charge on oxygen, and I'm seeing that that negatively charged oxygen would love to find something positive or partially positive to attach to. And I'm seeing a very polar bond here with a very delta positive carbon atom. So what I'm going to do is use the lone pair on oxygen to form a bond to this carbon atom. Remember I said great nucleophiles love to attack carbon atoms. And in the process, we're going to be kicking out a bromine as a bromide ion. And if you follow those electrons, knowing that this curved arrow here is the formation of a sigma bond, and that sigma bond is shown right here. Okay, we just formed a bond to this carbon backbone from the oxygen of hydroxide. Nucleophiles and electrophiles make up more than 95% of the reactions that we cover in this course all the way through to the end. So understanding or being able to identify nucleophiles and electrophiles is going to be key to your success in this course.